Hallo, it's dumplet here. Here's an item on number theory. Find all integer ordered pairs x, y such that x squared plus y squared is equal to x plus y plus xy. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. So here we have a diophantine equation, specifically a quadratic one, but the typical stuff we use, parity checking mod something, or maybe factoring, those might be the tricks we typically apply in diophantine equations, but those just start from nice observations. And this one, I noticed at the left-hand side, x squared plus y squared, it is a sum of squares, so it's going to be non-negative. So obviously, I have to make sure the right-hand side it's non-negative as well. So maybe some parity checking will be involved. So what I decided to do is try to check all the possible cases. Now, because the left-hand side is greater or equal to 0, I'm going to try to take the cases. And in the first case, let's just suppose both x and y are negative, right? If both x and y are negative, essentially I could have x to be a negative a, and then y to be negative b. And I'm going to set here a and b are both non-negative in this case. So, positive in this case. So a and b are both positive for my case over here. Now, all right, I'll try to rewrite the equation. The equation becomes a squared plus b squared is equal to negative a minus b plus ab. And let me just put the terms with the negative signs in the front. A squared plus b squared plus a plus b, that's going to be equal to ab. All right, now we do have the very interesting Amg inequality, right? The Amg inequality. Now I'm motivated to use the Amg inequality because we do have a condition of ab, and because I could relate a squared plus b squared with the ab over here. Because by the Amg inequality, the arithmetic mean of two positive numbers, again they're positive in this case because a and b are positive, so the arithmetic mean of a squared and b squared is going to be greater than or equal to the square root of a squared b squared, or the geometric mean. Well, this is just essentially ab, so I know that a squared plus b squared over 2, that's going to be greater than or equal to ab. But we know ab is essentially this thing over here, so I know that a squared plus b squared over 2, that's going to be greater than or equal to AB, which is essentially this one. I'm just going to copy. And I could subtract a squared plus b squared over 2 from both sides. I'll just have 0 greater than or equal to a squared plus b squared over 2 plus a plus b. And here is where things get interesting. A and b are both positive, so this is positive, this is positive, this is positive, but we're saying that 0 is greater than or equal to the sum of 3 positive numbers. Contradiction. It's impossible, so our assumption is wrong. So this case is actually impossible. So both x and y cannot be negative, right? So again, I'm just doing some parity checking. And first case is done, and then the second case, I'm just going to suppose one of them is negative. Now let me just make a statement here. I can say that x and y, essentially they can be interchanged. So for example, if xy will work, then obviously yx would also work. So I'm just gonna assume that y is going to be the one that's negative, which is in turn going to give me that x is non-negative. All right. So again, x and y can be interchanged, but just to keep my calculation simple, I'm just going to make y to be the negative 1, and then I'll do a similar substitution, y to be negative a, and then a is going to be positive. Okay, so the equation here just becomes x squared plus a squared is equal to x minus a minus ax. And I'm going to put the negative terms to the other side, just similar to the first one. So x squared plus a squared plus ax is equal to x. Now, we know that a is positive, but well, we're talking about integers over here, so I can say that a is greater or equal to 1. So that's going to tell me that this portion is greater than or equal to, right? So the underlined part is greater than or equal to x squared plus 1 plus 1 plus x. But this underlined portion is simply equal to x. So I have this equation here, sorry, inequality for x. And following from this one, I'm going to get, so subtract x from both sides. 0 is greater than or equal to x squared plus 1, which is just 2. And again, similar reasoning. We're going to have x squared here. Okay, that's non-negative, but 2 here is positive. So the entire thing over here is going to be positive. 0 is greater than or equal to a positive number. Contradiction, it's impossible. So our assumption here is also wrong. So the first case, both being negative, that's impossible. The second case, one of them being negative, that's also impossible. So the conclusion is that none of them are negative. So we're going to have x and y to both be non-negative. All right, so we would have the conclusion that x and y are both non-negative, right? There we go. Now, because there are nice theorems that I could use if x and y are both, let's just say, positive, let me just get over with the negative, the solutions that involves 0. Because, for example, I could use the Amg inequality if I have x and y to be positive. So let me just get over with the solutions that involve 0. Again, because of the argument that x and y are symmetrical, the equation is symmetrical, I could interject x and y. I'm just going to set y to be 0 for now, and then I'm just going to switch x and y in whatever solutions I got for this case. So if y equals 0, I'll have x squared is equal to, well, essentially just x. Okay, so I'll have x squared minus x to be 0. Simple quadratic equation. I could factor things out over here. So I'll get from here that x is 0 or 1. And then combine it with the fact that y is 0, I could list down all the possible pairs of x and y. So 0, 0, and then 1, 0. But with the symmetrical argument, that's going to bring us another solution of 0, 1. So these are the only solutions that involves one of those two variables, x or y, to be 0. Right? That's going to be this case. And then for my last case, I'm going to try to induce the AMGM into my solution because I do have the condition that x and y are both positive. Okay. Now, by the AMG inequality, a very similar result from the previous one. I have x squared plus y squared divided by 2 is greater than or equal to xy. So I'll have x squared plus y squared greater than or equal to 2xy. And then for some of you guys, this can also be derived from x minus y squared being greater than or equal to 0 with the simple fact that a square is non-negative. So you could also try to use that. But this will be the result that I'll try to use because x squared plus y squared is equal to this thing based from the given. So x plus y plus xy is greater than or equal to 2xy. So I'll have, let me just put everything to one side over here. 0 is greater than or equal to xy minus x minus y. And I would want to try to solve x and y over here. So what I'm going to do, I'm going to copy this again. So 0 is greater than or equal to xy minus x minus y. Now here is where the factoring trick might get involved because we do have xy, x and y, and whenever we see these three terms, so two variables and their product, we are motivated to use the Simon's favorite factoring trick, or you could just apply, this is just a very simple application of the factoring by grouping. Again, it might be obvious to some, it might not be obvious to the rest of the people, but what I'm going to do is I'm going to add 1 to both sides, and then I'm going to factor the right-hand side here by grouping. First two, I'm going to factor out an x, and then the second one, I'm going to factor out a -1. And essentially, I'm just doing factoring by grouping. 1 is greater than or equal to x minus 1 times y minus 1. And this is a very interesting result because, well, x and y are integers based from the thing, but we want integer solutions, and they're both positive, so there is a restriction for the value of this one to be less than or equal to 1. This can only be 0 or a 1. Alright, that gives us a very interesting result. if the product is 0, so product being 0, we're going to have here x equals 1 or y equals 1, right? That must be the case if the product is 0, right? We want x to be 1 or y to be 1. And then in the other case, if we want the product to be equal to 1, the x and y are positive, so the only possible case is when x equals 2 and y equals 2. So this is going to generate a solution already, 2, 2. So that's good. And we just have to finish the cases for x equals 1 or y equals 1. Again, because of the symmetry, I could just try to substitute y equals 1. I'm going to switch x and y to get all the possible solutions. So I'm going to go back to the original equation because this is going to be our basis. And I'm going to take care of the case where x equals 1 or y equals 1. But then again, just because of the symmetric fact, I'm just going to say y to be 1. And I'll try to solve for x. So x squared plus 1 is equal to x plus 1 plus x. So the 1 cancels out. So x squared equals 2x. So x squared minus 2x is equal to 0. So x times x minus 2, that's going to be equal to 0. I'll get here x to be 0. I'll get here x to be 0. Or x is equal to 2. But obviously the x equals 0 case is impossible because we're taking the case of x and y to be positive. So I'm going to ignore the x equals 0 case and only have x to be 2. All right. So y equals 1 is going to give x is 2. So this is a solution. And because of the symmetry, that's going to generate to me another solution, 1, 2. Right? So 2 solutions for this one. We have another one here. So 1, 2, 3, including these 3 from the rest of the cases. 6 solutions in total. And those are the 6. Right? So 0, 0, 0, 1, 1, 0, 1, 2, 2, 1, and 2, 2. These 6 will be our final answers. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.